Welcome everyone. I'm June Adams, CEO of PowerCalc. We're thrilled to have you here today for our second webinar on PowerCalc. We've just launched our graphic, automatic, and simultaneously generated one-line diagram, the first one-line in real time on the planet. We demonstrated the one-line in depth in last week's seminar, which is now posted on our YouTube site. Today, we'll be reviewing the one-line and also giving you an overview of some of PowerCalc's other functions: voltage drop, fault current calculations, and AIC ratings. PowerCalc is patented software. With 7 million plus equations, it calculates the entire power distribution system automatically, and changes are instantaneous upstream and downstream across your design. The 3 inputs per circuit are load type, load kVA, and number of poles. This bottom-up approach makes our software incredibly accurate, as actual values are used and not estimated values. And all calculations are in compliance with the National Electric Code, or NEC. Now I'm turning today's demonstration over to James Khalil, president of our company and inventor of PowerCalc. We ask that you hold your questions until the end of the presentation. This is an open forum, and we welcome questions about PowerCalc, electrical engineering, the NEC, or your own projects. So let's get going, and here's James. Thank you.
So good afternoon, everybody. This is James. Today we'll be using one of the projects that's on file, as we did last time, for the Atlantic West Elementary School. That is one of the schools that we're working on with the largest school district in Florida for Broward County. So let me start by getting there. So you know that you need to go to your project list and then select the project that you are working on. So the project we're working on right now is Atlantic Online. So you start with the project information. As you can see here is Atlantic Online project. And I just had to name it this way, so when I make a change, something like that, I'm not actually affecting the main file for this particular project. Now you can also here, you can edit any of this information if you want to. So now we're going to go directly into the project control panel. As we demonstrated last time, this here is the entire power distribution system in that particular building. Actually, it's a partial of it. I had to simplify a little bit for the sake of time and for this demo. Last time we talked about the one line and how important it is. So I'm going to go ahead and click on the one line to show you a picture of it, or a graphic of the one line, which was created automatically as you go line step by step. So here's a picture of the one line diagram. You can scroll, you can zoom in and zoom out, and all of this in here was generated for you automatically as you go and input the circuit into the panel. So, as part of the quick review of PowerCalc, as you all know now, that all I need from you is the 3 inputs, and we have generated a wizard for that. So, if I go again back to my power distribution and select a panel, we open the panel. The panel consists of all these circuits in it. I do a little bit. As we always say, that the way we build up the panel is circuit by circuit, and we start from the bottom up approach. And all I need from you for any circuit to come up with the correct values for the branch circuit is 3 inputs. Input number 1 would be the kVA. It doesn't have to be in that sequence, but input number 1 is going to be the kVA, and then the number of poles. You can click on it. It'll be a pull-down menu, and then the type of load, what we call it the MAC load. And this particular one, we selected R for receptacles. If you're looking for a legend for all the type of loads, it's going to be at the bottom of the panel, at the footer, down here. I'm going to take you to it. So you see, as I scroll down, there is the MAC load legend down here, to the all the way to the left, and R stands for receptacles, L stands for lighting, and so forth. So that will give you an idea on all what all these macros mean. And these are very important, that you have to identify the type of load, because the NEC distinguish between different type of loads, which is primarily if it's resistive load or it's a motor load. So you can see here that we have a lighting, we have a power load, which is resistive load. Anything that is not a motor load would be considered as a resistive, okay? And then you have the motor loads. And the calculations is going to vary, or the requirement of the NEC for calculating the branch circuit characteristic or values for that particular branch circuit is going to be different from type of load to another. And then also, it's very important to choose the type of load, because that will also apply to the demand loads. So the NEC has different demand factors for different type of loads, whether it's a receptacle or lighting or a motor load and so forth. Okay. So how do we get to the one-line diagram? As I said, circuit by circuit, bottoms up. You build up the circuits in the panel. The panel gets built up automatically for you, and the header of the panel will get adjusted automatically as you input these specific loads. Now, how do we enter each of these circuits? As I said earlier, we have put together a wizards. I'll take my picture right here. If you go back to the control panel of that particular panel that you're working on the right side of it, you will see several buttons, which are the functionality that are associated with that particular panel. You can see at the bottom here, there are 3 wizards. Wizard for the panel board module, wizard for the branch circuit module input, and wizard for the erase. Last time we talked about the wizard module for the panel and the branch circuit. So to input any of the branch circuits, you click on the wizard, and then you can go ahead and go circuit by circuit. So this is now circuit number 1, or you can select any circuit that you want to input directly right now. So let's say we want circuit number 8. Right now, all these values are filled in already, I guess, from the previous the previous seminar. And also lists for you what the characteristic of that particular circuit. If we change the load, see here, if I go ahead and change the load from 1.2, say to 4 kVA, and enter. It will automatically change these values after a little bit. Now the system is calculating all these for you. So we can go ahead and close, and that circuit now is reflected on the panel schedule. Give it a little time here to update. While the system is updating in the background, I mentioned there are 3 wizards, and which is again the panel module wizard, the circuit input wizard, and then the erase. The erase, there will be a separate seminar on the erase wizard and it's something to give you to maximize the ultimate value for the circuit, to give you the best performance in terms of energy savings and reducing the losses, the heat gain losses into that particular circuit. As I said, we would have a separate seminar for that. So now we generated, again, circuit by circuit, generated a panel. From the panel, now we can go ahead and connect that panel upstream to the power supply. So if you go into the upper left corner, you see that panel 3P. It's an existing panel, and it's fed from transformer T1. If we want to change that feed, you can go back and select, take it out of that particular selection, and say we're going to actually feed it from panel K. So we click on K. It says available circuit. There is no available circuits for you, so we'll have to go ahead and find another panel. Okay. So let's go ahead and connect it to the bus, FPL bus, and the only available circuit for us is circuit number 6. We're going to go ahead and click on it and submit. I need to close some of the open files in here to speed up the resources, or have more resources for the seminar. Okay, so we'll feed up some of the resources here, so to speed up the process. So what else can we talk about the one-line diagram? There's special functions that are associated to the one-line diagram. So before you really can finalize the one-line diagram, there are 2 or 3 other functionality that is supported by PowerCalc, is the voltage drop, and then the available fault and the fault current calculations throughout the entire power distribution system. Again, as I said, it's supported by PowerCalc, and if you go back here to the control panel, click on the one-line diagram. If you remember, we moved panel, I believe it was P3, from the transformer T1 to the FPL. So here it is. As you can see, it moved it and updated all the other associated value with it. So this here is a balanced one-line diagram based on the engineering calculations and the NEC requirement. The only information that is missing, it would be the fault current, and of course, once you perform the fault current calculations, it also set up the value for the AIC, the amperage interrupted capacity, which is very important in order for us to have a fully protected system. Amperage interrupted capacity is based on if everything goes haywire, whether it's on the panel or close by the panel, that extra energy that is going to go and pass through this panel towards the fault is a tremendous amount of energy. So the panel has to be designed in terms of the bolts and how it's all being constructed to sustain that much power and energy going through it during a fault. So it's very important that we have to run the fault current calculations, and that will be the worst condition if it happens, and that energy has to pass through the circuit breaker or through the panel. It has to be able to interrupt it and isolate that particular fault without causing a lot of damage upstream, downstream from that particular fault, and also protect the space and, of course, the personnel that's in that space. To initiate the fault current, I would like just to mention one more thing in here. The electrical service is actually from FPL, the Florida Power and Light, from the power company. It was estimated at a 1500 kVA transformer. These are values that you need to get from the power supplier, whether what is the size of the transformer or what is the available fault current at the primary side or the secondary side of the transformer provided by that particular power company. So let's exit the one line and let's go back to the application. Part of the application, if you look at the power distribution here at the top row, it has the project information, the E node, and then the short circuit calculation. So let's go ahead and click on the short circuit calculation. Okay, so what you see in here is a map of the entire power distribution system in like a spreadsheet format kind of thing. It will outline the enclosure type on the left side. This is all the panels that are associated with this particular power distribution system. And then separated by the total on the panels. And then you go to the next enclosure type, which is going to be the distribution panels, again, in that power distribution system. And then if you keep scrolling down, the third type of enclosure, it will be the building equipment. And it's an entire summary for the entire power distribution system, so you don't have to go from one panel to another or from one building equipment to another. You can go ahead and print this or view it on the screen. It will give you such information, information such as, so this panel here is panel 6C, is fed from MDP3, and it shows you the total connected load, the demand load, the percent impedance for that particular load on the feeder or on the transformer, if there is a transformer. And then if you scroll to the right, it will show you the panel board in terms of the feeder on the secondary side of the transformer that is feeding the panel. And then if there is a transformer, it will also show you the primary side of that transformer. So these panels right now, there is no transformer. So it's just showing the direct feeder from the supply panel, which is the MDP, to that particular panel, and it shows you the feeder calculations. Now, it doesn't show you right now any fault calculation because we have not started that yet. However, it does show you some of the AIC ratings on some of the panels, and the reason it shows it here because these values were overridden or the automatic calculation was taken out because this is an existing facility, so we knew what the AIC rating of that particular panel. But so we set it up manually, but we have not performed the calculations yet. Now, on the top of the short circuit calculation sheet, there is this input banner here, which titled short circuit calculations. It has two methods, the automatic method or the manual method. So what's the difference between the two? The auto is you go ahead and say, if you know the transformer that's feeding this particular facility, and as I said, it will show at 1500, so I need to go ahead and select the 1500. If I select the 1500, and of course the line voltage is at 480, and it's a three-phase, it will automatically calculate for me the available fault current at that particular transformer. So I need to go ahead and I guess notice the 18,000 in here. That was based on the 300 kVA transformer. So now, excuse me, if I calculate that value went up from 18,000 to almost 51 or 52,000 short circuit available current at the transformer. Okay, so that's how you start your fault current calculations. We'll in the next seminar we will go into depth in what would be the next step and so forth. But what I wanted to show you is how to initiate that calculation. So we showed today if it's an automatic, what happens, and then if you did not know the transformer size and you contacted the power company and the power company gave you the value of the available current, short circuit current at the transformer, you can go here and say, well, I'm going to go ahead and put it manually. And let's say that is, they give us and say it is 65,000. So we can go ahead and say 65,000 and then calculate. So now it changed the value from the 51 to the 65, and that would be your base point for the calculations downstream all the way to the last panel on the power distribution system. Still, we don't have any information in here because we need to input one of the most important item in terms of calculating the fault current. It is distance sensitive. So we still have to go from one panel to another and put the estimated length of the feeder. Okay. Now, the other value or the other calculation that we need to perform that will also affect the output of the short circuit calculations and the AIC ratings of the panels would be the voltage drop. Why the voltage drop needs to be performed, especially on the feeders, because, as I said, the fault current is sensitive to the distance and the type or the size of the conductor. So the voltage drop also will determine the size of the conductor, whether the calculated value that we calculated is adequate or not. So if it is not, to maintain the voltage drop value, we would have to adjust the conductor size. So adjusting the conductor size will also affect the fault current calculations. Now, so to perform the voltage drop calculations, let's go to one of our main distribution panels. It is not mandatory really to perform the short circuit, the voltage drop calculations by the NAC. The NAC just make a recommendation to perform the voltage drop, and it makes it, and they would like that the voltage drop percentage to stay within a 5%. And they, I guess the industry standard to break that 5% into two segments, a voltage drop on the feeder and a voltage drop on the branch circuit. So the voltage drop on the feeder is up here. So that's the feeder for that particular panel. If we go up here under the feeder, this feeder has 5 sets of 400 in 3.5-inch conduits. If you go a little bit to the left, it will show you what is the voltage drop set on, which, as I said, that it's recommended by the NEC to have 2% on the feeder and 3% on the branch circuit. So if you look at the top of the panel at the voltage distribution system, it shows a 2% at the feeder and a 3% down here at the branch circuit. I kind of highlight. Sure, this went away. Okay, so here's the 3%. So the system by default will give you that voltage drop calculations and will recommend to you what is the maximum distance associated with that particular voltage drop. Again, this is an existing condition, so we actually set it up on, I believe it's 50 feet. I'm going to go ahead and take that out and put it back on automatic. So if we go to the voltage drop, I'm going to go ahead and take that 50 out. I'm sorry, from here. Okay. See, now it changed that 50 into, in order for me to maintain the 2% voltage drop as recommended by the NEC and most of the building officials, I can actually travel 1,847 feet and I was still within the 2% voltage drop. On my branch circuit, if there's a branch circuit here, which if we go to the number 1, my branch circuit, which is a single odd, to maintain the 3% voltage drop, I can go up to 708 feet. Okay, so the system is already doing the required calculations based on the recommendation automatically for you. You really don't have to do anything. Now you can adjust that as you go in your design. If you're not happy with the 1,847 feet, say it's longer or shorter, you can always adjust that, and then the system will go ahead and adjust the voltage drop or adjust the feeder for you to maintain that particular voltage drop. Okay, so this is in a nutshell today. Because of the time, I need to open the floor for questions if there's any questions. We will go into details in the next seminar and so forth about the fault calculations and go have an actual example that is done manually, and then we'll go ahead and implement that on PowerCalc and see and compare the values, and then let you know how you can adjust if you're not happy with the fault, current available, and the AIC ratings that system comes up with, how you can actually play with these numbers to adjust it, of course, legally, and to give you the results that you are looking for. And with that, I will open the floor for questions.
Can you hear me?
No, I don't.
Okay, I have a question. Can you explain to us what over design is and what under design is?
Our industry, I guess, before the automation and having software programs, transformed from the engineering calculations or the mathematical calculations into the rule of thumb kind of thing. Okay, I've done it once, I've done it twice, I know exactly what the output is going to be. Not realizing that there is a lot of other parameters that's actually going to affect the size of the conductor, the size of the conduit. One of them would be the ambient temperature. Most of the circuit that we design are, say, rated for 30%. 30 degrees Celsius. So yeah, I can, apply the rule of thumb. Yeah, I've done it 20 times or whatever. So the result is going to be the same. Not realizing that now the ambient temperature will actually affect the capacity or the ampacity of the conductors. So you didn't actually run your calculations adequately and per the NEC, you're either going to be undersizing the conductor or oversizing the conductor. So by having a platform like PowerCalc that automated all these processes for you, all you have to input is the load and the load type. It will give you the precise size and values to size the conduit, the conductor, the quantity of them, to perform at the utmost efficiency that would meet the NEC. And also gives you capability, if you want to override it, you can go ahead and override it. So by having a platform that designs to a specific value that is mandated by a code like the NEC, you're always going to be providing what is actually required to provide the circuit or provide the power to that particular circuit. So you did not oversize or undersize. And of course, when you oversize, that's a lot of cost that is on the project that is not being utilized for anything. So you increase the cost of the construction. If you undersize, you actually having the risk of starting the fire. That circuit breaker is going to always trip, or it's not going to be able to provide the required power, and maybe start a fire in the facility. So again, it's a hazard situation. Okay.
I know that you were recently caught into a project where there was an issue of over designing. Can you tell us a little bit about that and what the potential cost savings were for the customer?
Well, thank you for reminding me of that. It's a project that we got involved in, designing just really the emergency power to this facility. The facility it's 160,000 square feet. I guess an exclusive club, country club facility, and it was designed by the engineer. And in order for me to design the emergency power requirement for that particular facility, to add the emergency generator, they gave me a copy of the original facility drawings, which was still under construction. So when we start interfacing with the design, we look at the one-line diagram, looking at some of the load calculations. What caught my attention that it's 160,000 square feet facility, and it has about 20 transformers in it, step-down transformers from 480 to 208, and they're all the same size. And in my almost 40 years experience in this city, I've never designed a facility that had all the transformers to be the same size. So that kind of, raised the flag. So as I dug deeply into the facility, into the design, we discovered that yes, it was designed by, I guess, another software which they don't use the bottom up approach. They use the top bottom approach, where you set up the values of your panel, the values of your transformers, and then you start loading the panel, and hope to God that you're not going to exceed that value. So they set up the transformer sizes, all of them on the 112 kVA. Now, once they did that, also that affected also the construction. Anything according to the NEC, if the transformer is 112, or actually over 75 kVA, the room has to be that house that transformer has to be designed with a fire rating of 2 hours. That's very expensive. So that added expense to the project, or unnecessary expense. So they set up the transformer at 112, and then they start loading these transformers with the load. And we found out that the maximum was like 30 and 45. So we went back to the developer, I guess, and to the owner, and showed them the problem. And that so they went back and asked the engineer of record to redesign the facility based on our recommendation, and that saved about $2 million, a little bit over $2 million just in the electrical distribution equipment. Of course, unfortunately, they already have built the rooms with the 2-hour rating walls, so they couldn't really save any money on that part. So that was money wasted for absolutely nothing. And that's a result of an over designing that put $2 million or $3 million on a job that you would not actually utilize anything out of it or see the benefit of it. Okay. Any other question? All right. I guess with this here, we conclude this seminar for today. And next week, we will meet again and talk about or elaborate a little bit more on the short circuit calculations, showing an exact example that's hand done, and also we'll compare the time that took us to do it manually versus how much time it took us to implement that into or include that into PowerCalc. With that, thank you very much, and hope to see you next week. Goodbye.